All right, let's go ahead and get started, I guess. Yeah, hi everyone. I'm Barak. I work at CoreOS and I work on Torus, which you may have heard of. If you haven't heard of until now, well, welcome, because you're going to hear about how it's built and what's going on. Yeah, so a little bit about this talk. We're going to talk today about storage in general, storage on Kubernetes. Motivations, what do we have going with Kubernetes, where we're at. What's the dream? What is we actually want to build on Kubernetes when it comes to storage? What is Torus and how does it work? Actually, we'll dive into some implementation choices and some details. And then talk a little bit more about how we could, what sorts of things, what is it we want when we want to integrate storage with Kubernetes? So kind of a weird question, but who here has deployed a cluster the hardware way? I mean, I know Kelsey Hightower did the hard way, but what about the hardware way? Good, lots of hands. That's actually better than I was expecting. I mean, how many people pixie boot their own servers in like their closet? Or a rack if you have one at work, I suppose. Point being, setting up storage on these things once you kind of get going was one of the first things I noticed when I was setting up my server. That wasn't immediately obvious, right? Because it's all about the big three: compute, network, and storage. In any sort of cluster environment, this is what we care about. So compute, we know this. This is Kubernetes. This is what we're all here for, is how do we distribute compute across a bunch of nodes in a cluster. Interestingly, you'll notice that it also uses etcd as a coordination point, as a lock server by which all the API calls and all the objects live on and survive in the cluster. And so then there's network, which, hey, we have CNI for that, Container Network Interface, if you haven't heard that acronym, which is an open community platform to abstract network between lots of pods. Particular implementation of this canal, which we use a lot of CoreOS, uses, again, etcd as a lock server to coordinate which IPs go where. So that's kind of a, interesting pattern. What about storage? And no, not everything is stateless, much as we would like it not to be, right? So you've got a mess of options when it comes to Kubernetes. This is just from the docs, the various volume plugins we have baked into Kubernetes as is today. And well, so let's take this moment and have this whole daunting list. Let's back up. What is it we need? Right? What do we need out of storage on Kubernetes? Well, if we go way back to the basics, right? This is something you probably all saw in CS classes or books on CS before, which is as you get closer and closer to the CPU, you have higher bandwidth, lower latency, but you can't store nearly as much. And what we kind of want, right, behind this all, is after system RAM, after local storage, is distributed mass storage, a place where our bits can live in perpetuity that may or may not be on our local host. And there are two main categories for this, right? Block storage and object storage. Block storage being sort of volumes for pods, the way we think about them today. Available anywhere in the cluster would be nice, right? And should be as easy as host path or empty dir, which are built in, like the things we see in all the examples for Kubernetes, how you run applications that have some state. They usually sit in a host path or under empty dir. And wouldn't it be great if we kind of had EBS in the Amazon world, but everywhere? Because like a lot of hands were showing, we want to run this on bare metal. We don't have the wheels of Amazon behind us. And then there's object storage. Similarly, applications built to understand buckets, things like S3 or cloud storage, a little bit of HDFS, which we have dealt with before if you've been managing servers for a long time, which usually has really great throughput. Like I can just write as fast as I can blast to the network, but limited semantics on what I can possibly do to this file. It's not necessarily always arbitrary read-write. Sometimes they're append only. Sometimes you've got some other constraints. But importantly, it also gives you the ability to have multiple nodes in a cluster, read and write the same things at the same time, which is really handy for a lot of different, especially data processing use cases. So wouldn't it be great also if this was easy to run as a Kubernetes, replication controller, deployment, daemon set, anything you like. We already do this for kubedns. It's one of the things we tend to install first when we first have a Kubernetes cluster running. We also do this with monitoring. We do this with the API, whatchamacallit, kubeproxy. There's a handful of things that start up on every node once you get going. And if it were an open community platform to abstract persistence, across a cluster of servers using etcd as a lock server, following the rest of the pattern that we have been noticing. So what we'd really, really want, right, is some sort of magical file pointer. Something in the cluster that stored bits that was distributed, sharded, replicated, error detected, error corrected, versioned, encrypted, and available everywhere. That's the goal, right? That's the thing we want, is to be able to build. So, and we want it to be one kubectl away, right? We want to be able to just launch this upon creation of, we've pixied our machines, we've got Kubernetes up and running, maybe it's self-hosted, maybe not, other talks we've been giving this conference. But it should be just as easy to go kubectl create -f storage and make it work. And so that's why we created Torus, right? We were trying to push into the envelope and push into this white space of what can we build that is this easy to use under Kubernetes. Kind of a missing piece of the platform if you think about compute, network, and storage, all based, for consensus reasons, on etcd. So, and what have we built? Well, we're getting close, actually. In the sort of minimum viable Torus, it is distributed and sharded and replicated and detected, not corrected yet, versioned and available anywhere. So we're kind of building out the things that we kind of want. So now let's talk a little bit about what is Torus? How does it work, right? It's, I'd love to give a live demo. I'm happy to do that after if people want to see it, but I'm a little nervous to give really good live demos at KubeCon. So, general overview, right? What goes into Torus? Where are some of the moving parts? So, as with many architectures for storage products in general, there's consensus and the metadata being run through etcd. And then we draw kind of a very hard interface here, which is any sort of metadata or agreement upon the state of the world needs to go through this Go interface up to etcd. And this kind of takes the place of a metadata store or a mon or something similar. It's used for discovery of peers, coordination, checkpointing of data, knowing where the data checkpoints are, keeping track of volumes and sort of all the small but important data relating to the state of the world, except for the whole bulk data itself. The server abstraction is just kind of the entry point for main. We create a Torus server. It can be a client, it can be a server. Server is kind of a misnomer. And this is the thing that allows you to open one of these magical file pointers. That's it. It is a view into the distributed platform. This is also where we can track, monitor it, heartbeats. This heartbeats up to etcd, saying I'm alive, I'm here, I'm using whatever resources I'm using, I'm providing whatever resources I'm providing. And below that, it needs to be able to get blocks for this file that it's just handed you. So underneath it is kind of the distributor layer. And I named it after kind of like a distributor cap in a car, which is the way that each block can be fetched peer-to-peer over gRPC, and then also on this layer keep track of what storage lies underneath it, which is just a key value store, nothing kind of fancy down there, or appears as one. And then also replicates or GCs based on the state of both etcd, the metadata coming from above, and the messages it's receiving from its other peers. Right. So, what is inside one of these files? I said the server hands you a file. How do we achieve some of these magical file pointer aspects? Which is that first inside of a file, every file has one of these inode structs. Since it's append-only view of the world, which is to say that once one of these things is written, it's never rewritten. It's always only ever replaced. And so an inode over a file over the span of its life will be replaced by multiple previous inodes, so that creates the chain there. And then also keeping track of which blocks are in this file, a list of blocks of a fixed size. Default is 512K, but that's actually configurable at cluster creation time. And above each of these blocks is an abstraction. We could have just a list of blocks, and that would be a fully cogent file. But we could also have a list of CRCs for each of these blocks, and we can check those. We can also have a subset of these blocks having an error correction block. We can also have each of these things have an encryption key. We could also have an arbitrary abstraction that to the consumer looks like a list of blocks, but below gets checked and fetched, possibly from other servers, or generally looks like a list of blocks. And so as these things kind of progress, we have v1 of the inode being replaced by v2 of the inode upon the sync call. Sync being one of my favorite syscalls, because that's when you are probably lied to by your underlying storage, but just for speed reasons. But that's actually where we try and have a contract, right? Is to say that when I fsync something, it actually got written, theoretically, to the underlying storage. And in the same way, that's when etcd will be updated, informed of a new version printed. The inode is no longer mutable at that point. It's fixed and sent out everywhere. And the way then that works is that if you've changed a block inside of an inode, say you've gone from green to blue, the new block's data will also be sent out as soon as it was received. Just the reference gets changed. We sync. And the data still lives out there until finally the rebalancer comes along and sees, oh, hey, I have this block which is no longer alive. It's no longer referenced by inode 2. And that second data block there is ready for garbage collection once every node has checked in with etcd and knows that the latest version is 2. If it still thinks it's 1, it can hold on to future versions. That's cool, because it's still in the future, and we don't know to delete it yet, and we shouldn't, because it's coming from the future, coming from possibly unwritten state. But if it was old, we know it's time to go. And then, OK, how do we go ahead and distribute these things? So we've built up a file abstraction. We can keep our blocks in our storage, kind of key value below us. How do we go about actually distributing them? And so the way Taurus does it is with consistent hashing for rebalancing. And this is kind of a fun little twist of kind of put on the standard model, which is this. If you assume that there's a peer function, the hash ring, one that takes any reference for any block and gives you a full permutation of all the nodes in the cluster. That could be hundreds possibly, but for the moment, let's look at 4. And with a replication layer of 2, that means that the first 2 are read. That's where the block should live, is on those first 2. And it should always live on the top n of the resulting list. Now, we can do 2 things, which are kind of awesome. We can change this function. And when we change this function inside of etcd, say we add a node, perhaps our hash function has changed. Perhaps it hasn't. We can try and tune that function. A peer function will put it out. So that means you can actually kind of write anything that is guaranteed to have the same output. But now suddenly node 2 and node 4, which had that block before, node 2 should still have it, but node 5 is really the next one should have. So how do we go about rebalancing this? So here's our state, and we've gone ahead and added the new node. We've changed the function. Each of these functions has a version. Each one's immutable. Each one gets updated from etcd, the same way that an inode might. And node 4 looks around, sees it has its block. It's always checking itself, and says, hey, I have this block. The new hash function says I'm rank 3 in this. It should be 2. Hey, does 2 have it? Oh, no, 2 doesn't have it. Over peer-to-peer. Here, node 5, please have a copy. Node 5 gets its copy. It's like, oh, thank you, node 4. And now 3 copies have it. And then when we come back around again, this is also then garbage collection, which is node 5 sees it, says it's happy, make sure node 2 has it. Node 2 checks node 5. And node 4, once it's finally done checking itself and seeing that everyone who should have this data has it, is free to then delete it. And ta-da, we've kind of rebalanced our cluster and changed where this piece of data lives by changing a peer function. Now that function can be, and this is kind of one of the more, not out there, but like directional ideas we're thinking about, is being able to kind of combine multiple functions. If we can think about a function that kind of takes 2 of these rings and creates another ring out of it, as long as it has a consistent way of going about it, we can start to do things like rack awareness. Right? We could say only things that have this rack should be at the front of the list, or things that are in this data center, or you can have SSDs or have a certain speed. There's a lot of different parameters you might want to have on these things, tags, labels, and Kubernetes. But at the end of the day, you could have functions that build on the other functions and compute these things, which would be really cool. So how is it kind of working with Kubernetes? I know I'm going a little on the faster side, but that's all right, because mostly I like questions. Yeah, so how does it work with Kubernetes? Well, in the docs, there's an example for running it as a daemon set, which works, or you could use an RCA or a deployment. Interestingly, the storage node's identity, it gets minted when you create the data directory and lives with that data directory. The fact that the process itself is running is kind of arbitrary. If that process were to die, if you were to reboot the machine, everything you need lives in the data directory. So as soon as it comes back up, it just presents that same folder, for lack of a better word. Either as data directory or a physical disk. We actually have a PR for that too. This will also happily use the new etcd controller that we at CoreOS we've been talking about this past week. If we can spin up and manage and have self-managed etcds, that kind of creates our metadata story. We can just deploy an etcd controller specifically for Taurus on our cluster, and then deploy all the Taurus nodes that connect to this etcd, and then we connect. In some sense, it's a service designed to bring a host path or some other local item per node into the distributed world. So that's its job. How did it actually connect to these things? Is well through FlexVolumes, which are, I'll get back to this in a second. How the Taurus, if you haven't used a FlexVolume before, it's how other pods can use Taurus or any other arbitrary binary for volumes. It's just right now an exec interface, which means that the kubelet shells out, runs your FlexVolume binary in it, runs your FlexVolume binary mount with some options. It does nothing special other than exec with the appropriate interface. But this is really kind of a pain to update, because if we have this binary on each host, we have to actually put that binary on each host somehow. And hey, wouldn't it be great if we could do that through containers? Because hey, we deliver binaries to hosts all the time. So in fact, that's a little bit of what we're thinking about. I see a lot of people here from SIG Storage, hi, is that we're moving a lot of the storage plugins in that list I showed you out of process. That's kind of the general plan from Monday when we all met, as well as having a proposal for quote unquote Flex 2, which is an actual RPC API over a channel, be it a socket, a TCP socket, a Unix socket, something that can grab a container from the internet and then provide an endpoint by which mounts can happen through that binary that lives in the container, controlled by the kubelet, which will actually talk to the socket endpoint and send the commands. Similar, instead of execing, but just running something else. And then, I forget if it got into 1.5, but dynamic provisioning for FlexVolumes. If it doesn't exist, it will, which is awesome. It's calling create and delete, as well as mount and unmount. But being able to provision new volumes, cut out new sources of data for FlexVolumes. So, yeah, kind of wrapping up, we need at the least, somehow, maybe it's Taurus, maybe we're building the white space, maybe we're building it wrong, maybe we're building it right. But we need at least a straightforward, software-defined storage solution one kubectl away, so that we can, even if we have better hardware for like your database server needs a specific new hardware that you pay a lot of money for, there's a lot of little stateful services that could greatly benefit from having generic available storage on every cluster that wanted it. And so software-defined storage should be free and open source. I see no reason why it shouldn't be. Yeah, that's the bulk of my talk. Taurus is at CoreOS, github.com/CoreOS Taurus, and now is a great time for questions, and I have a mic for that too.
I apologize. Hello? Is this coming up? Okay. Test. All right. I apologize if you answered this at the beginning of the talk. Do you suggest using this for production today, for precious data?
No, short answer. It's, at this point, even kind of behind closed doors, only a year old, and it's only been out in the public for about 4 or 5 months now. Obviously, we're working on it. That's my team's goal, and we're growing my team, which is good. So hopefully, our goal is in the moderate future to start saying beta, which is to say, yeah, load some, perhaps not mission critical, but data you'd like to see persist live. But as for trying it today, you can obviously just try it and see if anything works at all, which is where we're starting.
With the flex volume, how does the data actually present itself to the pods? Is it object store or is it file?
Data is presented as a mount, however mount happens, and it's completely up to the flex volume binary to do that.
So I can use a block store inside the pod as well.
Yeah, or it could use like a fuse driver or something. It just has to be able to, given a directory, mount whatever it means to into that directory.
And going back to the production use, are there other things on your roadmap or check marks that you're looking at to, like, is CRCs like the last thing that you want before you kind of trust a little more? Or?
Really the thing before we trust a little more is to do more dog fooding internally and to do more kind of torture tests. Right? Instead of have things that die intentionally. We did this a lot with etcd. That was really helpful for making sure etcd was fairly stable. And furthermore, because of that, we can trust etcd a lot more for Taurus as our metadata store. So setting up the same sort of thing for Taurus, and then yeah, that's kind of what that.
How does Taurus handle like network segmentation now?
It would mostly it causes read errors at the time of segmentation, right? Unless it was on the happy side of the partition, and it would try and go and replicate or rebuild. Go to the other replica, go to the new other blocks it needs to rebuild if it were to fail. But yeah, if you can't get to the data, you can't get to the data. So it's kind of a okay, yeah, what else are you gonna do? But as for talking to etcd, if something checks out for a little while, it'll mark unhealthy. It's not unlike how pods get rescheduled actually.
And I guess last question is what kind of latency or throughput do you see with?
Throughput, just direct blast some bits, do a DD to a block device, or just copy a whole image up. Pretty much saturates gigabit, at least as much as we have in my little test environment. As for like random small IOPS inside of a block device, that could be better. We're improving that. It's about 100-ish now, which isn't great. 200 is like a good Rust spinning disk, so that's a good goal. That's kind of what we would want to get to, is about 200 before we can say, like, yeah, okay, you can use it for any case you'd want for like slow but available storage.
So how does this compare to the existing cluster file systems that are supposed to be used in cloud systems, specifically Ceph, which seems to be eating everybody else's lunch?
Specifically Ceph, because there seems to be I'm glad you mentioned that, because the reason I think Ceph is, and this is kind of my own conjecture, quote unquote, eating everyone else's lunch, is that they went through the trouble about 3 years ago of actually going to writing a Paxos implementation inside of their mon. That's something that things like Gluster have not done. And so you'll notice that I'm pretty general about...
I think you need to explain Paxos for the audience. It's a cluster consistency model.
Just saying Paxos isn't enough. Okay. Just implementing Paxos isn't... anyway. So having some sort of multi-host, highly available, but strongly consistent metadata store is something that every distributed system like this needs, in my opinion. And that's why something like... I didn't. When you split brain, yeah, we'll talk offline. But yeah, so having something like that so that you can guarantee which side of a partition, say, wins. That's really kind of the sort of case you want it for, is for a split brain, which is why I'm not sure about Gluster, because I know that split brains are kind of really painful there. And so yeah, why not just kind of go with Gluster? And the answer is that it's massive. If you want to have it, I met some interesting folks at this conference, the Rook.io folks out the door, who have been repackaging Ceph into something that could be containerized, which I think is actually a really kind of cool idea. Just that the notion being that it should be easy, it should be open source, and that's kind of where we should go with it, period. And As for Ceph and why, now I'm kind of lost my question.
Why this, not Ceph?
Why this, not Ceph?
If I'm a customer, sell it to me.
If you're a customer, sell it to you. Because it's way easier and we're focused on doing kind of the things that you need for Kubernetes. And if someone else is able to achieve that, great, because open source is what we're all here about, right? Kubernetes is open source, even though we have different vendors doing lots of different things. At the end of the day, we can get pretty far with Taurus because etcd we know works as a consensus store, and the rest it's a separable problem, right? Instead of trying to build the whole world, we're trying to build just half the world. It's still a hard problem, but it's at least I'll give it the old college try. So. And maybe we can move faster as a result. Maybe we can do other cool things. Like, it's amazing how much of the magical file pointer you can actually put together once you know that the consensus store is actually there for you. So. More questions? Wrap up early? It's 1:02. Cool.